And the plan for the remaining 2 hours, 2 hours and a half is to that I keep going through this presentation of the sector couple or the other sectors in PyPSA-Eur. Then Fabian does a small tutorial, and you have time to try it. And we'll also be around the room to help you and discuss with you problems or questions that you might have. So we stop right here before the lunch, describing the different, the representation of the different industrial sectors. And I want to make it short, so my ambition is to provide you with an overview of the different, of the infrastructure, including when the different sectors are modeled. And a good place to start is with the modeling of other networks. And we can start with the modeling of the gas network. So as with other sectors, there's a lot of data processing. In this case, the gas network is coming from a previous project, the SciGrid gas dataset. It includes nice information regarding the capacity of the pipelines, plotted here, color-coded by the capacity, but also the location of entry points because of their LNG terminals, because of their connection to gas pipelines outside Europe, or because they are points where fossil gas is extracted. Also some information on where gas can be stored. And then there's the representation of how the gas is flowing. And I think we were having this discussion this morning. There's no representation of the real physics that govern the movement of a gas in a pipeline, right? So the Weymouth equation that says the mass flow relates to the pressure difference at the extreme of a gas pipeline in a nonlinear way, so the terms are quadratic, is not represented. But the gas pipelines are more links that have a certain efficiency that can represent the electricity demand to do the compression to counterbalance the pressure loss when the gas is kind of moving or traveling through the pipeline or some leakages. So is this a simplified way or a linearized way of representing gas transport so that the whole big optimization problem can remain linear? There's also a very nice option that allows to retrofit some of the existing gas pipelines into hydrogen pipelines. And this has a certain cost that are coming from the European hydrogen backbone studies, but the cost of retrofitting an existing gas pipeline into a hydrogen pipeline is lower than, let's say, building a hydrogen pipeline from scratch. So you can include this in analysis that relates to where and how much would it cost to build a hydrogen network in Europe. All right, so this is kind of the, yeah?
Is there any consideration for hydrogen mixing in the gas network, or is it just gas or retrofitting?
So currently, the default is either gas or retrofitting into hydrogen. We don't include blending strategies. Cool. Then where can we potentially store hydrogen in the future? This is another data set, in this case coming from this nice paper that includes estimation of the existing salt cavern where hydrogen can be stored underground. This is one of the options of storing hydrogen. The other option is to store hydrogen underground on steel tanks, but the cost is radically different, right? It's roughly 20, 30 times more expensive to the NE capacity if you are storing hydrogen on a steel tank than underground. So then it's interesting to have access to the potential of underground hydrogen storage. And this can be useful, for instance, when investigating elements such as hydrogen doing some seasonal balancing, so you really want to or need to have a large demand. So a large energy capacity. So how does this work is that we have the data set with the existing potentials, and then we aggregate that on the regions that we are using depending on the clustering that we have selected for our network. So the clustering, the number of nodes and regions that we are selecting has been decided initially, has been used to cluster the electricity network, to represent the heating demand, all of this, and it's also used to calculate the underground storage potential for hydrogen. And there are three categories. So the estimation for underground potential is calculated at a offshore location, onshore location, or nearshore, meaning location that are, I remember, 20, 30 kilometers closest to the shore. And the user can select which of these potentials wants to use, either the three of them or some of them, right? And this distinction is because there is some, could be some potential environmental concern if you are using onshore salt cavern and how to do and how to dispose the brine, the salty water. So by default, it's selected the near shore, but the user can select which potentials to use. All right, so that will be the another part of the representation of the infrastructure. Another key element that also has an important spatial resolution is biomass. So here I'm talking about, I'll be talking about biomass potential, and then biomass is being used for different usage in the model. Some of them are exogenous, like we saw in the industry demand. If there is a cement manufacturing facility in some of these places, set up an exogenous demand for biomass. But there are other demands for biomass that are endogenous, such as it will be, let's say that it's cost effective to install a combined heat and power plant that uses biomass and produces electricity and heat somewhere. So that will create an endogenous demand for biomass. So what I'm showing here are not the demands, but the potential, how much biomass can be utilized in every region. And the database that we use is this Espresso database from the Joint Research Center that has different categories of biomass. So what is happening in PyPSA-Eur is that the different categories are classified into three groups. And this classification is based on for what is used the biomass in PyPSA-Eur. So maybe it's easier if I start with the potentials not included. And this is because in the Joint Research Center and Espresso database, some of the biomass potentials are coming from what is called energy crops. So crops that are cultivated to produce bioenergy and could compete with food crops. So the default assumption is that we do not include those potentials. If you think that those potentials should be considered, you just change the config file. Then, out of the potentials that we don't include, we have what we call solid biomass and biogas. Solid biomass includes all the types of biomass that are solid, and they mean that they could end up being combusted. That could be residues from agriculture, residues from forestry management, right? Biomass, whose main purpose, at least initially, is to be combusted, although there are, PyPSA-Eur includes the option to also model the possibility of gasifying that biomass and end up doing gas product out of that. This is also typically called like woody biomass. And then we have categories that can end up being or transforming into biogas, and the classic example is manure, which later in PyPSA-Eur can be upgraded into methane. Again, which of the categories described in the Espresso database that are later aggregated into solid biomass, biogas, and not used is selected via the config file. And other than that, in the Espresso database, there are three scenarios that calculate potential for a low, medium, and a high biomass deployment. And which of these scenarios from the Espresso database is selected can also be selected in the config file. Yeah, so this is the general overview, and then as I was, yes? Yeah. So this the if so the potentials are calculated in two categories. This will be solid residues from agriculture. This will be manure. This creates solid biomass. This creates biogas. And then if you want to use solid woody residues from agriculture and convert them into or gasify them, you can do that through a technology represented in the model via a link, and this has a certain efficiency and a certain cost. This element, this production of biogas, let's say, it's because biogas and biomass in general has many different details, but the production of the transformation of something that is straw, woody, and needs to be gasified, it can be done, and it's represented by a technology that is gasifying and producing this biogas from biomass, from solid biomass. It's split, right? What I'm saying is that this will be more the representation of manure, and this will be more the categories that are woody, solid, and need some additional gasification. And then when you have the potential for biogas, there is another link or representation of the technologies that is doing the biogas upgrade into methane with its cost, efficiency, and all this. All right, this is kind of the overview of the biomass. Let me then use a few slides to talk about.
I just had one question on the previous
slide. Sorry.
Do you also segregate between biogenic carbon and fossil carbon when you try to calculate the carbon budget on this atmosphere level which you talked about? You have differentiation in the type of carbon in the model as well?
So some of the technologies that can produce, let's say you want to produce methane, right? You can produce it with CO2 that has been captured from the atmosphere, and then it goes through a specific process to be combined with hydrogen and to produce methane. Or you use a process in which you are using biogenic CO2 combined to hydrogen, and then converting that into a synthetic methane with biological origin for the CO2. Yeah.
But like when you put carbon budget, is there a difference between how much of the carbon budget is biogenic carbon and how much of it is fossil carbon?
The CO2 constraint is imposed globally on the whole model, on all the CO2 emitting technologies without considering its initial origin. All right, so let me go a little bit through how the carbon is managed. So capture, transported, store for a short time, and then sequester or store for a longer time. So if we start with capturing technologies, the model includes what is called direct capture, standard solid solvent based technology that can be freely installed in any location and is consuming electricity, some heat to do the regeneration of the sorbent, and one of the standard process. But CO2 can also be captured from point source, so from all the locations where there is CO2 emitted in a high concentration, and that includes industries, so all the process emissions when cement is produced, and all the other process emissions, but also from point sources in combined heat and power plants using biomass or using fossil fuel, such as methane, for instance. So this is where it can be captured. Then it can be transported through pipelines that can be built on purpose or from scratch. And by the way, all these networks that I'm describing, they can be activated or not activated through the config file. So you might want to understand if there's a benefit of transporting hydrogen. And here you might want to understand if there's a benefit of transporting CO2 or not. Or you could maybe say, I don't care about this, I'm just going to deactivate this network to make the problem easier. And then once it's captured, and this is the option of transporting, you can, or the model can store for a short time in a tank, or it can sequester underground for a longer time. And I will present some of the details in the next slide regarding the sequestration. But the other option that you can do with the CO2 is to produce synthetic carbonaceous fuels as the ones that I presented before lunch, so including synthetic methane via the Sabatier process, synthetic oil via these Fischer-Tropsch, or synthetic methanol via methanolization units. And this is one difference, I would say, with many other models, or at least many big integrated assessment models who have traditionally modeled just a specific combination of these technologies, such as BECCS, bioenergy with carbon capture and storage, in which they put together CO2 is being captured from this generator that uses biomass, and it's captured here and it's being sequestered here. So the whole technology is doing this negative CO2 emissions. Here, what we model are different technologies, each of them doing one part of the process. So effectively, if you have a direct air capture and a sequestration, you can get negative emissions. But we don't assume that these things, we don't assume technological combination, but let the model decide there. A little bit on underground sequestration. Yeah?
Do you mind a question regarding this slide? Also, because you are producing synthetic fuels, it is possible to, are they also used, for example, regarding the transportation model? Let's say if you want to use CO2 to produce methanol, then methanol to olefins, and then all methanol to gasoline, that gasoline can be used also in the transportation model?
So in the transportation model, or in any sector, there's a demand for, let's say aviation. No? We say there's a demand for kerosene. This demand needs to be fulfilled, and this can be fulfilled with a fossil fuel or with a synthetic fuel. Yeah, this needs to be fulfilled, but at the same time, the CO2 global constraints needs to be fulfilled. So it could be that in some cases you have the two technological options, but because one of them will be less cost competitive, or it will be very detrimental for attaining your very ambitious CO2 global constraint, it's not selected, right? So I'm just saying that the selection is based on cost competition together with the penalization of the global CO2 constraint. All right, so CO2 sequestration potential. First, let me present the physical potential calculated based on this CO2 stop project and database. And similarly to other elements, in the config file, it can be selected which of the scenarios of this database is selected, either if gas fields, oil fields, aquifers, or the three of them are selected, and if the potential for onshore or offshore are selected. One of them or all of them, right? This will give you the existing physical potentials for underground sequestration. But because we know, and there's a lot of kind of scientific literature on all of this, that in order to attain the global CO2 constraint, having an option that gives you or allows you to have negative emissions is typically an easy way to find the solution to the problem. And we also know that this technology has some environmental risk and some uncertainty, right? We give the option to be a little cautious on the solution by imposing an additional limit on the annual sequestration. By default, this 250 megatons per year. This is more an ad hoc limit to avoid that we end up with solutions that rely strongly on using CO2 sequestration, right? Because, and by the way, we know that this is one of the elements that the system is very sensitive to, because it's a strategy to attain CO2, the global CO2 constraint, or a strategy to do offsetting of other sectors whose transformation could be difficult, such as aviation. But a nice way of using these functionalities is that, as with all the other assumptions, the user can run sensitivity, changing this parameter, and understanding or trying to evaluate how this affects the rest of the system configuration. Cool. So a quick summary of many of the things that I have been mentioning: exogenous and endogenous decision. And this kind of represents the state of the art of the model that what you can use today. So things that you, as a modeler, need to choose, and that you can choose in the config file. The level of energy services demand, the level of heating demand. You can assume things like we are going to live in bigger houses, so we'll increase our heating demand. Or we are going to, yeah, whatever. The share of district heating, right? I explained before that we have regions where they have high population density, so district heating could be used. But you could also say, I don't think that in this country or in this region we are going to have district heating to its full potential because of the other reasons, right? So you could always select to which degree the usage of district heating is fully allowed or disallowed or something in between in every region. The usage of how is the road transport, right? I mentioned before that you can select which percentage of the road transport is using electric vehicles, fuel cell vehicles, or internal combustion engine vehicles. Either if you use kerosene for aviation or the fuel. Either if you use methanol for shipping, hydrogen for shipping, oil for shipping, whatever you are using. To what extent the different sectors in the industry are electrified, and to what extent recycling is reducing the need for virgin materials in the different sectors. And to what extent some transformation in the industry, such as the production of steel via direct reduced iron and electro arc furnaces are used. You can also select this via the config file. And then what's happening internally? What's the model deciding in the optimization? How is the electric generation fleet changing, right? So what is the capacity mix to produce electricity? To what extent is cost effective to reinforce the transmission network? How much storage do you need of the different categories? We say here short and long duration, but you can have, if you give in reality you're saying how many batteries, hydrogen storage, or other types of storage, and you can independently optimize the energy capacity and the charging and discharging capacity. Also, all the technologies producing heat for space and water heating, together with the building renovation and together with the storage in that section. All the conversion technologies producing gas, methane, methanol from combining or using power and combining hydrogen and CO2. All the supply of process heat from industry, and all the elements related to carbon capture, right? Do I do direct capture, or do I do capture CO2 from point sources such as combined heat and power? And then are the two, in general, the need to supply the demands in every sector, plus the global CO2 constraint, which is taking the decision. Yeah? So trying to be short on the answer, the global CO2 constraint is a constraint, is an equation that also has a Lagrange multiplier or KKT multiplier, whose interpretation is that this needs to be the price of CO2 or the tax that you put in the CO2 in order to get the same solution or the solution that fulfills the constraint. So if you put a CO2 price equivalent to this Lagrange multiplier, you get to the same result. But another way of looking is what is this, and this is something we do, what is the CO2 price that I will need? And how does it compare to the current ETS market? Right? And roughly speaking, to reach fully decarbonization of the whole Europe, we are typically getting CO2 prices in the order of a few hundreds of euros. 400 euros could be a good reference. A little bit far from the current ETS.
I was curious because your numerical detail on all sectors and so on, you have a lot of existing data, so does it match the actual ETS price somehow, or try to see if you could also like, simulate the ETS market?
Well, the thing is that the current ETS market does not achieve the decarbonization of all these sectors, right? So that's why if you model, to model reality, you need to not asking for decarbonization of all these sectors. And we know that some of the sectors that I'm mentioning here are the ones driving the CO2 price high, such as requesting to decarbonize aviation, shipping, industry, things like the CO2 sequestration potential has a strong impact. So as I think it was also mentioned before, PyPSA-Eur has been conceived more for a modeling of a scenario that attains full decarbonization and trying to learn how to get there. There are now more and more applications bringing a model to today's system and trying to reproduce reality. I think if you only aim at decarbonizing the electricity system, you get CO2 prices that are closer to ETS. So below the 100 euros ton of CO2 reference value. And yeah, we do many things like this, like plotting how CO2 price needs to evolve to attain full decarbonization of other sectors. But I'm happy to keep discussing with you more offline. Any other question? Yeah?
Can we go to this transportation slide? So like in some of these, in the hydrogen balance, I can see some of like offshore pipelines for to transport hydrogen. So are they like really offshore pipelines, or they are just connecting their links which connect two nodes?
Like this one, right?
Yeah.
Offshore pipeline.
It's an offshore pipeline.
Because the routing is optimized. It's not like a net view.
Yep.
You see that, for example, between Spain and France and Germany, there's this pipeline route that is empty, where the routing of the pipelines is empty, optimized. There's no kind of point.
Okay. So like you have two options then, so you can either install offshore and onshore.
You give a predetermined set of connection options to the hydrogen network that is oriented around where we currently have electricity, gas pipeline connections. It's just a way to achieve a relatively good mesh network without including all possible combinations of connections between nodes, which would blow up the computational side.
Okay, now, thank you.
All right, I'm gonna try to be a little brief on the next slide. Because we have energy balance in every node and for every different energy carrier, we get a KKT multiplier that can be interpreted as the price of hydrogen or heat or electricity in every hour, in every time step that we are modeling through the year. And we also get energy balances. This is an example for the electricity, but we get the same for every energy carrier. And this is something that by default, in some of the carriers is plotted at the end of solving the simulation, so you can get an understanding of what's going on. And these prices are, I saw before, figures for the different time steps, but these prices can also be plotted And you also get them for every region in which you are selecting to model your network, right? I'm just going a little bit quick through that. These are very nice tables from the latest paper that Fabian drove that we mentioned before, in which I'm not going to read them, but you can go and see, how can electricity be produced and what is using that electricity? Some of these things are exogenous and some others are endogenous, and you can do the same with every carrier, right? So it's more a checking lists. And I want to use the last 5-10 minutes to discuss some other dimensions. One of them is using different weather years. That was also mentioned yesterday, right? And we mentioned we used 2013. And this is some analysis of the full sector coupled model, but it's now being solved with all the different, with 60 different weather years. You can see how the system cost is changing. And yeah, the change is about plus minus 10%. 2013, I don't see it now, but I know it's around, here it is. So not in the middle, but a little bit in the upper part of the configuration. Generally, the results are very consistent, a lot of wind and solar, electrification of heating, hydrogen to produce synthetic fuels, but some differences. And I think we learned from here that we need to use more than one weather year. Some of them are very easy to use, just changing the selection in the config file. Some others require downloading the weather data and reproducing the wind time series, solar time series, coefficient of performance time series, and all of these things. It can be done, it just needs storage and time for downloading the data. And then I just, to end, I want to also briefly mention different modeling options that you can select with PyPSA-Eur. So we have mainly 3 different ways of modeling the system, and you can roughly use the 2 of them very easily, and the 3 of them is under development and has some computational challenges. One is what we call overnight, and this just means that I'm gonna ask PyPSA-Eur to co-optimize the full system on a certain horizon. It can be, it doesn't need to have a time reference, because the horizon, I'm just deciding this based on the CO2 constraint. Let's say I'm asking the model to co-optimize a European sector coupled system that is net zero in emissions. This we call overnight, meaning as if you build the whole system in one night. Then we have a possibility to model pathways. So if we want to reach that point, let's say that that point is taking place in 2050, do we optimize the full pathway in one go? And this is called perfect foresight. It means you have information about all the steps. Or do we model a pathway that is based on steps, so that I optimize 2025 and with only having information for 2025, and then later, based on the existing capacity, the legacy capacity for 2025, I do optimize 2030, and then I keep going. This is called myopic because you have less short-sighted. You don't have the full perfect foresight. It's more representative of decision-making and process, but from a theoretical point of view, it's less, or it's not as optimal as the perfect foresight. So these are the 3 options. This perfect foresight is currently under development. You cannot use it today because there are some computational challenges associated to non-linearity of the social cost of capital cost that you assume and things like that. Other than that, you can also select to include the existing technologies in what is called a brownfield analysis, the existing capacities, or do a more explorative analysis, building the whole system from scratch, and this is what is called greenfield analysis. And you can also choose the investment year. So you could say, I'm gonna find a carbon neutral system, assuming system cost, or assuming technological cost forecasted for 2050, or assuming cost of today, and see how things evolve. All right, and then if we want to do the myopic, please go ahead. So 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 the fact of just running 1 year at a time is that you need to find a good combination of temporal, spatial, and technological resolution that is computationally feasible. If you think, for me, it's super important to model 2-3 years together, so I'm willing to sacrifice, I'm willing to use 5-hourly resolution, but model 3 years ago, you can do that. And then in the myopic, you model 3 years that represent this period. And then with the capacities that has been optimally determined, these are saved. And then you model the next planning horizon that inherits the capacities that were installed in the previous time step. This is what the myopic, and I think this is not a PyPSA naming. It's a quite Is it? Oh, yeah, could be. I was trying to. No, I agree with you. I would just say in our defense, I think the naming in the discipline is very confusing. We call this more rolling horizon when we are modeling 1 year, or we are modeling 2 years, but only seeing a period for optimizing the dispatch within that year. We try to call it rolling horizon and reserve the myopic. But I agree. I also find confusing the way we talk about this in energy modeling. But here I mean your first explanation, right? Some years, you get some capacity. And just one second. If you look at how we do this in a rule base, what is happening is that, let's say one network is solved. This could be 2025. Then, let's say some existing capacities are added. So this will be the capacities that were already from 2020. This is creating the existing capacities in 2025, then the network is solved, then you add the capacity from previous taper steps, and you keep solving the network for every planning horizon, but inheriting the capacities that were optimized in previous time steps. So this is something that you cannot parallelize, because you need to run it in series. So the way it is currently done by default is that if you have a capacity that was there, because it was installed in a previous years, capacities only get decommissioned when they reach the end of their lifetime. It's not mandatory that you use them, but if you build them, the capital cost is still adding to your system cost until they reach the end of your lifetime. This is the default. You can always say, well, if we are planning to phase out with certain capacities, you can modify them. I think the easiest way is to, in the power plant matching database, to change the expected end of life. Instead of what is currently assumed, you modify that based on your plans for phase out. And then they will be phase out when they reach the end of their lifetime. But if they are there, but let's say there's a very strong CO2 constraints, so that they are not used, they are not forced to be used, but their capital costs will be added to the total system so that you can capture the sunk cost, right? The problem with the myopic is that you could invest in something in 2025, but later you don't need it. And you have done this investment because of your myopia, because of not seeing that the CO2 was constraint was going to be reduced. So this is included, captured by maintaining the capital cost of those technologies in the system.
And can you limit the installation of new coal capacity after 2030, for example? Just say, don't install new coal, but use the existing one until the end of its life.
I mean, you could do everything. And I think this is a relatively easy change to include. I would also say that we don't see new coal being installed. Just the CO2 constraint is always preventing this to happen.
Okay.
I think my personal view is that discount rate are a super important topic that we should be talking more about that. So very happy to talk about you, but the short answer, if the so for every in PyPSA there is a financial discount rate that is used to calculate the annualized cost of every investment, and this you can select that in the config file. Typically 7% is used for most of the investment, and a smaller 4% for distributed investment, such as rooftop solar. That's the financial discount rate to annualize the system cost. And then when we are adding cost at different planning horizon, you need to have a social discount rate. For the myopic, this is a variable that you select in the config file. I think the default is 2%. You can select any different value. One of the reasons why the perfect foresight is computationally difficult is because it's one of the nonlinearities is due to the social discount rate that changes the value of the different planning horizon when discounted. You can also select that in the config file, but anyway, perfect foresight is still not fully available. But I agree it's an important element, and you can select financial discount rate, social discount rate, both from the config file. Yeah. And by default it's not processed, but it's a little bit that distributed installation, such as rooftop PV, that is typically not driven by large companies, is already assuming a 4% by default.
The answer is always you can.
Yeah.
Marta said, I said at the beginning, you can always work around some filtering, but it's not a default feature that is currently supported. Kind of managing, it needs somebody to manage the technology.
And there's a lot of scientific discussion on whether it's sensible to do for future, assuming different discount rates for 2050 for different countries based on historical.
So there's a prominent series of paper rebuttal,
exactly.
counter rebuttal paper. I think it's now a series of 5 different papers of 2 groups arguing for one case or the other.
Yeah. Yeah. Yeah, sorry, I shouldn't have gone into that topic. So, not that I don't want to discuss, but because this is something that is happening in a function that is not available, let's discuss this offline so that I don't make this confusion even bigger. But happy to talk to you about that. Yeah.
And then see
I would say because the objective function is a total system cost. So again, most of the things you can do it in the default setting because of the objective function is in the total system cost. This is where you use your budget. The way of thinking of can I use this the same amount of money or a little bit more than that to do different things. This is going in the direction of exploring the near optimal solution of space of solutions. And there are some, there's already a well, optimized with MGS or slightly, or an available tool to explore this a little bit. And a nice paper also by Fabian on how to do that. If you want to be only, if you think you are a owner of a certain type of assets, but you don't have the perspective of the total global planner, then you can do it, but you need to have you need to derive your own constraint, right? That represent this sum of money. Yeah.
Does PyPSA has learning right in the model?
See, this is why not available by default, but there is a nice paper by Lisa where we are looking at perfect foresight with endogenous learning. The current way that learning rate is included is because all the cost assumptions for both the overnight and myopic are exogenous. And in this exogenous cost assumption, the database from the Danish Energy Agency is including some learning, and that's the reason why some of the technologies has a certain cost. But it is not endogenized, so the cost of a technology does not depend on how much capacity, on how much cumulative capacity was installed in the previous time step. That's only happening when you do this perfect foresight with endogenous learning. This is one example. The other classic example is it will avoid a situation in which by 2025 you install gas power plants because your CO2 allowance is below than today, but let's say maybe 30% of today. So you think gas could be part of the solution. You install it in 2025. It has a 30, 40 years lifetime, but 10 years later, because of the CO2 constraint is much lower, this is not competitive anymore. And you have what is called a sunk cost. The capacity is there, but you don't want to use it. But you still need to pay it because it cost is assuming 40 years of lifetime. And the commission that earlier has a cost for you. So you make these kind of errors when planning because you don't have full foresight for the planning horizon. Yeah. Cool. I think. Okay, I think I might cover this. Right, and then many of the options that I described can be selected in the config file, either in the default config file, or which is very, very long and has many options, but it's also because it allows you to do a lot of configuration, or through these scenarios in which you keep the main or the other options in the config file, and you modify only the options that you want to investigate what impact they have. And I think more than me keep talking, I think it's now time for doing some practical implementation. Let me see. Yeah, so I think we do a short live demo, and then we have time for you to try running PyPSA-Eur with the whole sector in your computer. Right?